Hello everyone, this is part 1 of Heapsort. So before we talk about Heapsort, we first need to know what is a heap. And even before we talk about a heap, we first need to know what is a complete binary tree. So in this video, we will talk about what is a binary tree and how to store a binary tree in an array. We will also talk about what is complete binary tree and what is so special about complete binary trees. So let's first talk about tree. So here in this example, we have a general tree where A is the root node and it have 3 children, B, C and D. Then B have 2 children, E and F. C does not have any child and D have 1 child, G. Then E have 2 children, H and I, and G have 4 children, J, K, L and M. And we can also say that G is the parent of J, K, L and M. Now we can also represent the file system of a computer as a general tree. So here we have the file system of a computer represented as a general tree. So user RT courses have 2 children, CS016 and CS252. And inside CS016 we have 2 subdirectories, homeworks and programs, and 1 file called grades. And inside homeworks we have 3 files, HW1, HW2, HW3. And inside programs we have 3 files, PR1, PR2 and PR3. So we can represent the file system as a general tree. So now let's talk about what is a binary tree. So in binary tree, a node can only have at most 2 children, and each child node is labeled as either a left child or a right child. And it is not mandatory for a node to have both the left child and right child. So a node can have either the left child or the right child or none of them. So here we have examples of 5 different binary trees. Each have 3 nodes. And here we have examples of different binary trees. Each have 4 nodes. Now in this example, the binary tree on the left side is not the same as binary tree on the right side, because in the binary tree which is on the left side, D is the left child of B, and in the binary tree on the right side, D is the right child of B. So this is the reason why these 2 binary trees are not the same. So here we have an example of a binary tree where each level have the maximum number of nodes possible. So on the 0 level we have root node, on the first level we have 2 nodes, and on the second level we have 4 nodes, on the third level we have 8 nodes. So each level have maximum number of nodes that are possible in that level. So this is a binary tree where we have the maximum number of nodes possible in each level. Now let's talk about a complete binary tree. So a binary tree is said to be a complete binary tree if all the levels of the tree except possibly the last one have the maximum number of nodes possible, and if all the nodes at the last level appear as far left as possible. So we can see in this example we have 3 different complete binary trees, and all these 3 complete binary trees satisfies these 2 conditions, that all the levels except the last, possibly the last one, have maximum number of nodes possible, and all the nodes at the last level appear as far left as possible. So these 3 binary trees are complete binary trees because they satisfy these 2 conditions. Now the binary tree in this example is not a complete binary tree because it does not satisfy those 2 conditions, that all the levels except possibly the last level have maximum number of nodes possible, and all the nodes at the last level appear as far left as possible. So C should have a right child, but it doesn't have a right child, and J is the right child of F. So E should also have the right child, and F should also have the left child. So in that case it will become a complete binary tree, but in this current representation it's not a complete binary tree. Now let's talk about what is a full binary tree. So a binary tree is said to be a full if all its leaves are at the same level and every interior node has two children. So interior node is a node which is not the leaf node. So if it satisfied these both two conditions, so that tree will become a full binary tree. So here in this example, we have a full binary tree because all the leaves are at the same level and every interior node has two children. So in some textbooks, complete binary tree is referred as almost complete binary tree, and full binary tree is referred as complete binary tree. So there is a difference in terminology. Now let's talk about how to represent a binary tree using array. So we can store a binary tree in an array. So what we will do is we will assign the root node in number 1, and for any node if it have number I, we will assign number 2i to its left child and 2i plus 1 to its right child. So we will store the left child at 2i index in array and its right child we will store at 2i plus 1 index in the array. And if we have to find out the parent of a node which is stored at index I, we will find out by calculating I by 2. And if we have to find out the left child of a node which is stored at index I, we will calculate 2i. And to find out the right child of a node which is stored at location I, we can figure out by calculating 2i plus 1. So here we are storing a incomplete binary tree in an array. So we will start A with A. So we will store A at index 1 and then we will store B. So we will go level by level, and on each level we will store left to right. So we will first store A, then we will store B and C, then we will store D, E and F, then we will store G, H, I and J. But E does not have the right child, so there will be a gap. Similarly, F does not have C does not have the right child and F does not have the left child. So there will be gaps while storing this incomplete binary tree in an array. So to calculate the parent of E, now E is stored at index 5. To calculate the parent, we can calculate by I by 2. So 5 by 2, taking the floor value which is 2. So B is the parent of E, and calculating the left child of E. So E is stored at index 5. So left child should be stored at 2i, which is 10. So I is stored at 10. And the right child for E should be stored at 2i plus 1 at 11. But since it doesn't have the right child, this location is empty. That's why there is gap while storing this incomplete binary tree in an array. But when we store a complete binary tree in an array, there will be no gap. We will see that in the next example. So here we have a complete binary tree, and if we store this complete binary tree in an array, there will be no gaps. So again we will start with A. We will store A at index 1, then we will store B, then C, then D and E, then F and G, then H, I, J, K and L. So if we have to calculate the parent of E, so E have index 5, so 5 by 2, taking the floor value 2. So B will be the parent of E. And to figure out the left child of E, so left child of E should be stored at 2i. So E is stored at 5th index, so 2i will be 10. So we should store the left child at 10th index. So J is the left child of E, and the right child of E should be stored at 2i plus 1, which is 11, and the right child of J is stored at 11th position. So we can calculate the parent and the left child and the right child of a node easily if we store the complete binary tree in an array, and there will be no gaps. So this is the beauty of complete binary tree. So when we store a complete binary tree in an array, there will be no gaps. So this is the most important property of a complete binary tree, is that it guarantees that when storing the complete binary tree in an array, there will be no gaps. And when we talk about heap, because heap is a complete binary tree, so in the next video we will talk about heap and how to insert nodes into heap and how to delete nodes in a heap.